This is our first lecture for Chapter 19, Radioactivity and Nuclear Chemistry. So these are just some of the learning objectives we have for nuclear chemistry. First of all, we want to recognize the importance and the applications of nuclear chemistry. And we're going to look at 5 types of radioactivity: alpha decay, beta decay, positron emission, gamma ray emission, and electron capture. So with these 5 types of radioactivity, we should be able to identify each type and also write balanced equations for those processes. So again, we want to be able to write chemical equations that represent those 5 different types of radioactivity. And to do that, we must be able to write the chemical symbols and then balance those nuclear equations associated with them. Then we are also going to learn how to use the valley of stability, and we'll learn what is meant by magic numbers. And we'll also look at the kinetics of nuclear reactions. And one of the things that we'll learn is that nuclear reactions are first order reactions, and we'll be interested in the half-life equations associated with those first order nuclear reactions. And then lastly, we'll look at the mass defect as that relates to fission and fusion. So we're going to begin by looking at the discovery of radioactivity. So Antoine Henri Becquerel designed an experiment to determine if phosphorescent minerals also gave X-rays. Because he was looking at these materials and they were phosphorescent, so they glow in the dark. And he was trying to see if they would give off X-rays. And what he discovered, that certain minerals were constantly producing these penetrating energy rays that he called uranic rays. So they're like X-rays, but they're not related to phosphorescence. And Becquerel determined that all the minerals that produce these rays contained uranium. So this is why he called them uranic rays. And the rays were produced even though the mineral was not exposed to outside energy. Because with some phosphorescent materials, you expose it to light, and then later on it glows. But these minerals that he was looking at that had these uranic rays, it didn't matter if they were exposed to the outside light or sun. They always gave off this extra energy. So the question is this energy produced from nothing? So just trying to figure out where this energy was coming from. The Curies played a large role in determining what these uranic rays were. And Marie Curie used an electroscope to detect uranic rays in samples. An electroscope is just a device that you can detect these uranic rays with. And we'll look at what an electroscope is in a couple of slides. Now she discovered new elements by detecting their rays. And radium, the element radium, is named for its green phosphorescence. And polonium, which she discovered, is named for her homeland, Poland. Now, since these rays were no longer just a property of uranium ores, she renamed it radioactivity. So let's talk about what that electroscope is. So when charged, the metal foils, so we've got some metal foil in this flask. So they're charged and they've got positive charges on them. And since positive charges are on each foil, they're going to repel each other. So the pieces of foil are pushing away from each other. So when charged, the metal foils spread apart due to like charge repulsion. So here's an actual picture of an electroscope. And we're going to use thorite as our example. And thorite is a radioactive ore that contains uranium. And then when exposed to ionizing radiation, the radiation knocks electrons off the air molecules, which jump onto the foils and discharge them, causing them to drop down. So the thorite releases radiation. The radiation knocks off electrons from the molecules of air that are inside the flask. And then those electrons then go to the foil and neutralize the charge. So it goes from positive to neutral when it picks up the electrons. So that causes the foils to drop down because you no longer have like charges repelling each other. So let's look at some other properties of radioactivity. So we said radioactive rays can ionize matter. So like we saw with the electroscope, that radioactive matter ionized the air, which knocked off electrons, which then added to the foil to neutralize the charge. So this can cause uncharged matter to become charged. And this is the basis of a Geiger counter and the electroscope. Radioactive rays have high energy, and radioactive rays can penetrate matter. So an alpha ray can only penetrate to the skin, so it can be stopped by skin. And a beta ray and beta radiation can be stopped by aluminum. Gamma rays or X-rays can be stopped by lead, and the neutrons need very thick concrete to stop the neutrons. And then another property of radioactivity is that radioactive rays cause phosphorescent chemicals to glow, and this is the basis of a scintillation counter. So old clocks that used to glow in the dark had radioactive material in them that caused them to glow in the dark. So I just want to take this a little bit of time to review some of the things that you learned in Chem 1A. So some facts about the nucleus. First of all, every atom of an element has the same number of protons, and remember that's the atomic number Z. And then atoms of the same elements can have different numbers of neutrons. This gives rise to different isotopes. And if they have a different number of neutrons, then they're going to have different atomic masses. Now the isotopes are identified by their mass number. And remember, the mass number is the number of protons plus the number of neutrons. So atomic number is the number of protons, and that identifies which element something is. And then the mass number is the number of protons plus the number of neutrons. The number of neutrons is calculated by subtracting the atomic number from the mass number. So we don't need any redundant information. So if the mass number contains the protons and the neutrons, and we know the atomic number, which is the number of protons, we can simply subtract the atomic number from the mass number to calculate the number of neutrons. And the nucleus of an isotope is called a nuclide, and less than 10% of the known nuclides are non-radioactive. Most are radionuclides. Each nuclide is identified by a symbol. So the element minus the mass number. So we're representing X minus A. So if we're writing the symbol for the element, remember the element is represented here by X. So this is just maybe if we're talking about a helium atom, so this would be He. And the mass number, remember we said that was the number of protons plus the number of neutrons. And then Z is the atomic number. So that's just the number of protons. Radioactive nuclei spontaneously decompose into smaller nuclei, and this is what we call radioactive decay. And we say that radioactive nuclei are unstable. The parent nuclide is the nucleus that is undergoing radioactive decay, and the daughter nuclide is the new nucleus that is made. Decomposing involves the nuclide emitting a particle and/or energy. So whatever it's emitting, it could be either a particle or it could be energy or it could be both. All nuclides with 84 or more protons are radioactive. So anything such as polonium or higher is going to be radioactive. So let's just look at some of the atomic symbols that we'll be using in this chapter. So we have the particle in the first column, the symbol that's used to represent that particle, and then the nuclear symbol that gives a little bit more information about that particle. So the proton we represent by P with a plus sign, and as a nuclear symbol we can write H, because remember one proton is a hydrogen and it doesn't have a neutron, so it's 1 and 1. Or you can use the P to represent the proton. The next particle we're going to look at is a neutron. So remember that's a neutral particle, so we can write N0. And that neutron doesn't have any protons, so it's a 0 here for the mass number, for the atomic number, and a 1 for the mass number because there's one neutron. And then an electron we're representing with an E and a negative sign. And here we have an electron, and it has a -1 symbol, so it has an opposite sign of the proton. And an alpha particle, so we use the alpha symbol. And if we're using the nuclear symbol, an alpha particle is a helium atom. So there's 2 protons in the nucleus, and there are also 2 neutrons. So 2 neutrons plus 2 protons equal 4. So a beta particle, so we represent with a beta symbol here. A beta is an electron ejected from the nucleus. And we'll see this when we have beta decay, when a neutron becomes a proton. And a positron, so we don't have a different symbol for here, we just have the nuclear symbol. So the positron is like an electron, it has the same mass and things like that, but it has a positive charge. So we'll see a positron emitted when we have a proton being converted to a neutron. And then lastly, a gamma ray. This is just a lot of energy, so this is a gamma symbol. So there are no neutrons and there are no protons. We have a 0 and a 0 for both the atomic number and the mass number. So let's define what transmutation is. Rutherford discovered that during the radioactive process, atoms of one element are changed into atoms of a different element. So they call this transmutation, when you go from one type of element to another type during radioactive changes. So this is where Dalton's atomic theory statement 3 is no longer valid, because remember that one said that one element cannot change into another. Well, if you have a nuclear reaction, you can change from one type of element to another. And in order for one element to change into another, the number of protons in the nucleus must change. So here we have an example of a nuclear equation that shows us how we can have a transmutation process happening. So we describe nuclear processes with nuclear equations, and we use the symbol of the nuclide to represent the nucleus. And when you write nuclear equations, the atomic numbers and the mass numbers are conserved. So we use this fact to predict the daughter nuclide if you know the parent and the emitted particle. But if I know the parent nuclide is this uranium-238 and it has 92 protons in the nucleus, and I know that it undergoes an alpha decay. So if I know an alpha particle is 2 protons and 2 protons and 2 neutrons, I know that the sum of the mass numbers have to equal up together. So 238 on this side and 234 plus 4 on this side make 238. Here we have the number of protons of 90 plus 2, so that's 92. So it also equals the 92 for the uranium. So in the nuclear equation, mass numbers and atomic numbers are conserved, and we use this fact to determine the identity of a daughter nuclide if we know the parent and mode of decay. So here we're just showing the algebra of how we figured out what this ion was. So we're going to be looking at 5 types of radioactivity: alpha decay, beta decay, positron emission, gamma ray emission, and electron capture. So first we're looking at alpha emission. This is also known as alpha decay. And remember we said an alpha particle contains 2 protons and 2 neutrons. So basically this is a helium nucleus. And this is the most ionizing but least penetrating. So it's the most ionizing, meaning it knocks off electrons the easiest, but it's the least penetrating, so it can't pass through as many materials as some of the other types of particles can. Now, loss of an alpha particle means that the atomic number has to decrease by 2. So if we're losing 2 protons as we form an alpha particle, the atomic number for the nuclide has to decrease by 2 when it formed daughter nuclide. And if the atomic number decreases by 2, the mass number has to decrease by 4, because remember we have the 4 for the mass number of the alpha particle. So here we have radium-222, and the number of protons is 88. So if we're undergoing alpha emission or alpha decay, so we're producing an alpha particle, 88 minus 2 gives me 86. So I look on the periodic table, and 86 corresponds to radon. And then looking at the mass number of our nuclide, the parent nuclide, so 222 minus 4 gives me 218. So this is the mass number for the radon. So this would be a balanced nuclear reaction. So now let's look at beta decay. So an electron, a beta particle, is emitted from the nucleus. So this may seem a little bit weird to you. So you eject an electron that comes out of the nucleus. And when this happens, a neutron becomes a proton. So for example, if we're looking at a carbon-14 nucleus and we eject a beta particle, so that electron comes out of the nucleus. So when that happens, the mass number is staying the same. But what happens is a neutron becomes a proton. So the atomic number increases by 1, but the mass number stays the same. So again, the beta emission is a neutron changing into a proton, and it's ejecting an electron from the nucleus. So a beta particle is like an electron, but it's moving much faster and it's produced from the nucleus. And again, here is our symbol for a beta particle. And when an atom loses a beta particle, its atomic number increases by 1. So the number of protons increases by 1, but the mass number remains the same. So if we are looking at the beta decay of thorium, a neutron changes into a proton. So this is thorium-234. So thorium has 90 protons in it. So if we're undergoing beta decay, one of those neutrons is becoming a proton. So the mass number stays the same. We go from 234 to 234. So 234 plus 0 still equals 234. But that electron that's ejected from the nucleus, so minus 1 plus 91 equals 90. So the number of protons has increased by 1 since one of those neutrons became a proton. Next we have gamma emission. And gamma rays are high energy photons of light, and you have no loss of particles from the nucleus. So you don't have any protons or neutrons changing. You're just losing a lot of energy. So there's no change in the composition of the nucleus, the same atomic number and mass number. Now gamma emission is the least ionizing, but it's the most penetrating. So it's harder to ionize a material, but it's going to pass through more items than the other types of radiation. And this generally occurs after the nucleus undergoes some other type of decay and the remaining particles rearrange. Okay, next we want to look at positron emission. And in positron emission, a positron is emitted from the nucleus. And this is an instance where a proton becomes a neutron. So if we're looking at carbon-10, we go from carbon, which has 6 protons, to boron, which has 5 protons. So notice that the mass number is staying the same, but one of those protons has become a neutron. So the proton has emitted a particle that's about the same size of an electron, but it has the opposite charge, so it has a positive charge. So a proton becomes a neutron in a positron emission. That proton becomes a neutron and it's releasing a positron particle, which has a positive charge. Now in positron emission, a positron has a charge of +1 Cu and negligible mass. So we call this the anti-electron. When an atom loses a positron from the nucleus, its mass number remains the same, but the atomic number decreases by 1. Positrons appear to result from a proton changing into a neutron. So in this reaction where we have sodium-22 and we have a positron emission, notice again that the number of protons and neutrons, the total number, the mass number stays the same. So 22 and 22. But one of those protons becomes a neutron as we emit a positron. So we go from 11 protons to 10, and 10 protons corresponds to neon. So the last type of nuclear reaction that we're going to look at is electron capture. And this occurs when an inner orbital electron is pulled into the nucleus. And when this happens, a particle is not emitted, but the atom changes. So it's the same result as a positron emission. So the proton combines with the electron to make a neutron. The mass number stays the same, but the atomic number decreases by 1. So electron capture, the proton changes to a neutron because it's taking in the electron from an inner orbital, and when they combine together, that proton and the electron combine together to make a neutron when electron capture occurs. So an example of an electron capture reaction is with ruthenium-92. So it has 44 protons. When it takes in that electron from the inner orbital, and that electron combines with a proton, it becomes a neutron. So we lose one of the protons because it becomes a neutron. So we lose one of those protons as it becomes a neutron. So the atomic number drops from 44 to 43, and this is technetium. But the total mass number doesn't change. So this just summarizes the different types of decay. So an alpha decay, remember, produces an alpha particle, and an alpha particle is just an helium nucleus. And then we have a beta decay, so a neutron becomes a proton. We have gamma emission, so you're just releasing energy. So it's an excited nuclide. It's very excited, has lots of extra energy, and that energy is released as gamma radiation, and that produces a more stable nuclide. Then we have positron emission, where we have a proton becoming a neutron, and we emit that positron. So a proton becomes a neutron. And then electron capture, an electron from an inner orbital combines with a proton in the nucleus to make a neutron, and so a proton becomes a neutron. So the overall effect with positron emission and electron capture, the result is just the same, but it's the process that happens. So one is a positron emission and the other is electron capture. So embedded in this file are other videos that are helpful for understanding what's going on in this chapter. So if you want to stop this video and watch those other YouTube videos, you'll probably find them very helpful for aiding these lecture slides.